Okay, so let's continue. We are now in the spherical normal distribution. So the most important class of multivariate normal distribution is the class in which a random variable y is normally distributed with mean vector mu and covariance matrix sigma squared I. The normal distribution is spherically symmetric about mu. So if you have just the univariate case, you all often see this distribution with mu here and a variance sigma squared. So when you have in the multivariate case, or when your random variables now are in terms of vectors and matrix, you will have something like a sphere, no? So sphere na siya, three-dimensional. So I hope you can imagine how this normal distribution is viewed when it is already in a three-dimensional space or n-dimensional space. So ano na siya, kanang sphere, no? Or siya bola na in anig forma. Anyway, I hope you can imagine that. And the center part there is about the mean vector mu. So a rotation about mu is given by this transformation. So if we define a new random variable x where it is tau here is an orthogonal matrix, so you apply pre-multiply it by an orthogonal matrix such that this is satisfied. This is one characteristic of positive definite matrix, no? When you get tau orthogonal pod, tau prime is equal to I. And if you have this transformation here, that is x is equal to tau y minus mu plus mu, or actually what you are doing here is trying to make some rotations on your y. So this x, even if we transform it in basta linear lang na transformation, then x is still normally distributed. This time it is with mean mu and still variance covariance matrix sigma squared I, so that the distribution is unchanged, no, under rotations about mu. So we call this normal distribution with this covariance as your spherical normal distribution. So if the variance is just equal to 0, then we are sure that our y there is exactly equal to your mean vector mu, that is with probability 1. And it has this probability density function. So the spherical normal distribution will still have similar normal distribution that we have here. So the spherical normal distribution is the only multivariate distribution with independent components that is spherically symmetric. So now let's have a theorem that talks about projections, no, or the distribution of projections. So if our y is normally distributed, greater than 0 ang sigma square, then the projection of y onto v is also normal, no, with mean vector pb, or the projection of mu onto v, and covariance matrix sigma squared v. So if you recall, we always talk about if you have a space and if you have a vector y here, and then you have a space v wherein we try to project this vector onto v. So this is the projection of y onto v. If this is normally distributed here, if we can also talk about the projections or the vectors under this space V is also normally distributed. So we can always study y in the n-dimensional in terms of projections in your subspace V. Now, later, this concept is very important when we have multivariate vectors or n-dimensional vectors here, wherein it is very difficult to analyze in the n-dimensional. What we do is try to project it into a space such that ang kana na space two-dimensional na lang. One application of that is your principal component analysis. Now, principal components analysis usually writes the n-dimensional vectors here into linear combinations so that it still contains the information in the n-dimensional, but it is projected in a two-dimensional space or three-dimensional space, mas gamay na space na mas ma-interpret nimo kung unsay nahitabo sa n-dimensional. Okay, so the proof of this follows from lemma 3.6, wherein you have a transformation AY. So you started with Y, which is normal, say mu and sigma squared. So AY will still be normal with A mu, and then A sigma squared A prime, no? So the proof of that follows from 3.6C, and following that the projection of V transpose is just equal to that, and the projection of the square of PB is also equal to PB. So mo-follow na siya. Okay? So for example, kini mao ni imong PB, mao ni imong PB prime, but PB prime is just PB times PB, which is PB square, but PB square is PB. So mo nang mabilin, PB na lang siya. Okay? Of course, this is klaro, PB is your A. Next, letter B. So if B is orthogonal to W, then the projection of Y onto V and the projection of Y onto W are independent. So kung orthogonal daw si V and W, then the projection of Y onto V and the projection of Y onto W are independent. So to prove this, suppose we write Z as this will be AY, no? Where your A here is the vector PB and PW. So what we want is PBY and PWY, no? Muna na siya na itsura. And then we use the result na kung ang ato ang sigma 11, sigma 22, sigma 21, 12, sigma 21, kung kini siya or kini symmetric man na is 0, then we say that PBY, and so we look at the covariance matrix of PBY and PWY, no? So this is actually your covariance of Z. So kung kuhaon nato ang covariance ani man kini na off diagonal there is 0, then we say that it is independent. So to see that, so we just substitute it in this manner. So ang itsura ani mahimo siyang covariance of AY, no? So ang covariance of AY by previous result is A covariance of Y and then A prime. So your A here is this. So you have A covariance of Y, A prime. Okay, but the covariance of y is given by sigma squared. And then if you work on these two vectors here, get the result. So pwede ranin mo ipagawas, no, which is sigma square. So what is left is PB PW times PV PW prime prime, no? So when you multiply this one by this is this one, and then this one by this is this one by this is this one, and this one by this is this one. Okay, so but by assumption, V is orthogonal to W, so that the projection on V and the product of the projection on V times the projection on W is just equal to 0. So that is equal to 0 because the projection onto V is an element of V, and the projection onto W is an element of W, and they are orthogonal. So this is 0. So that we have shown that this is 0, therefore the covariance of diagonal entries of the covariance is 0. Then we use the result that follows that these are independent. So what theorem was that? What theorem did give that result? Anyway, you can scan through that theorem there. Basta mapakita nimo na kini siya is 0. Katong sigma 1, 2 is equal to 0. Next, we have, we start with a random variable y, which is normally distributed. Sigma square is greater than 0. Let V be a p-dimensional subspace. Then the square norm. So this is the inner product of is sigma chi-square distributed. So quotient man good ni siya because this is PBY prime PBY, no? Chi-square distributed with this non-centrality parameter, square norm of PB mu over sigma square. Now, to prove that, we have to find a variable such that kung atong z prime z, no, if you recall na kay z na normal man imong z prime z, this will be chi square, no? So to get this square norm projection, unsa day itsura sa projection. So ang atong gusto is may itsura siya ani. Now, if X is a basis matrix, di ba, ang PB is XX prime, no? Unsa na theorem gani? Because throughout, we assume that our X is orthogonal because it doesn't matter, dili man mo affect. So, kung orthonormal basis ang X, then we can always write PB as X prime X. So, ang atong So ang atong tumong na kung mangita ta og variable na kung atong kung atong z prime z x prime y over sigma, so z prime na nimo x prime y over sigma. Mugawa si ano, dapat mugawa si PBY square norm, no? So let us look. So actually before na itsura na siya, gi manipulate na daan pabali, no? Usually when we prove ay manipulate na ninyo daan pabali para makabalo mo kung unsay itsura ani in terms of x and y, no? So the flow of that is dinhi kini siya. Okay? So mao na igilit. So mao ni ang variable na imuhang i-manipulate. Remember na dapat sa para mahimong chi-square magsugod ka og standard normal, no? Normal 0, 1 or kung vector na ni 0 I, no? So you have to show first that x prime x over sigma will be normally distributed. Okay, so if this is your target variable na pagkuha nimo sa z prime z, mahimo siyang square norm sa y, no? Imo sana ipakita na kining z is normally distributed. Okay. So first we get the mean vector of z, which is the expected value of that. Now x is just a basis matrix or the normal basis. So it is a constant with respect to expectations. The expected value of y is given to be nasa assumption that this is normally distributed with mean mu and variance sigma squared I. So we have x prime mu over sigma. Yeah, let me call that V. And then since x prime x is just the identity matrix, this is actually theorem 2.6, no? When you have an orthonormal basis matrix, then x prime x is just equal to the identity matrix. So it follows that when we try to get the distribution of z, we want to get the distribution of z, you find the mean of z and the covariance of z. So sigma is just a constant. So the variance there will be 1 over sigma squared, and then the covariance of x prime y. So you can take it as a covariance of ay, where a here is your x prime. So the covariance of ay is a, covariance of y, then a prime. So it means that it is equal to a, which is x prime, covariance of y, then a prime prime. So that you know that the covariance of y is actually sigma squared I, and that will be a constant with respect to this matrix x prime and x here. So you will have x prime x, but x prime x is the identity. This is cancelled with that. So when you do multiplication, it's just I. So we see that z, which is x prime, okay, which is x prime y, sigma is normal with covariance mean vector v, but your mean vector v is x prime mu sigma. So this is x prime mu over sigma, and covariance matrix I. Okay, so you have this. And if you get the dimension of z, that will be a p by 1 vector. And again, you know that theorem 2.6c, and this is by theorem 2.6 also. Now we get your z prime z, or the square norm of z. So which is this. So this is just written by that. Application of prime, you will have y prime x, because x prime prime is x, then x prime, but this x prime is your PB, so you have their PB. And then since this satisfies, the z here satisfies normal, standard normal with v, so the non-centrality parameter here is v prime v and I. So kung imong i-square norm, may mo siyang chi-square, no? With this non-centrality parameter. So you will have mu prime PB mu over sigma square. So kay kini siya kay mu man eh, mu prime. So kini mu. So naa kay matrix PB. So y prime PBY over sigma squared will be chi-square distributed by previous result, no? So kung naa kay standard normal, imong square norm, chi-square na siya with centrality parameter. And again, PB square, which is PB times PB, is actually PB. So this PB here can be rewritten in this manner here, so that you can rewrite it as in this manner. Okay, mao man na imo ang gusto. You want the square norm of PB, which is PBY prime PBY, no? So to obtain this square norm sa PBY, you have to rewrite this in this manner. So this one is equivalent to that, because PB prime is just equal to PB. So kung imo nang isulat man na y prime PB prime man PB y, but PB prime is just PB, so y prime PB. So mobalik ka din, no? So that those are equivalent. So now we have shown that 1 over sigma squared, then the square norm of PBY is chi-square distributed with this non-centrality parameter, mu prime PB mu over sigma square. But mu prime PB mu, this one can just be simplified as the square norm of PB mu, or the projection of mu onto V by this. So from here to here, we know that we can write this as PB square, because PB square is just equal to PB, and here PB times PB, but PB prime is just equal to PB, so pwede nimo butangag prime, so that you can write it as the square norm. So it follows that substitution now, this one will just be, this one is substituted by the square norm of mu, or this constant can be placed adjacent to your chi-square. Then we are done. Question? So results used here is x prime is PB, then x prime x is I, PB square is just PB, and PB prime is just PB. No? So it's a repeated use of those results. Then as a corollary of that, So if we have an A, which is idempotent, so instead na PB na kay A na idempotent, so what is idempotent matrix is two conditions to be idempotent. One is A prime is equal to A and A squared is equal to A. No? So the same condition as your PB. So if Y is normally distributed with mean mu and variance sigma squared I, sigma squared is positive, and if A is idempotent and we know that the rank of A is equal to P, then A prime A is also chi-square distributed with this non-centrality parameter. So following the previous proof, this is just a corollary. Instead na x prime y over sigma, we substitute x prime by A, and you can verify that this is normally distributed with this parameter. The mean vector is A mu over sigma, and still the covariance matrix is the identity, so that when you get your A z prime z, no? So ay over sigma, which is equal to this, is also chi-square distributed. So the proof of this follows from the earlier results. And the condition, of course, that the rank of A is P. O na ang dimension niya sa imuhang chi-square or iyang degrees of freedom. So remark, the converse of the corollary is also true. That is, if Y is normally distributed and if A is a symmetric matrix such that this is satisfied, so the inverse man, so kung satisfy ni tanan, then A will be idempotent matrix of rank P. So ang bali ani na corollary, no? So ang bali ani na corollary, mo assume ka ani, may pakita na A is idempotent and of rank P. So the converse of that, so pwede siya if and only if statement, no? So the only quadratic form that have the chi-square distribution are square roots of projections. Quadratic form, no? That have chi-square distribution are square lengths of projection. This is your square lengths of projection actually. Because ang norm sa V, ang length man siya. So kung imong square lengths. Okay, next. Theorem 3.13, the book. So you still assume that Y is normally distributed with a variance greater than 0 or positive. You have two matrices, A and B. A is P by N and B is S by N matrices. And another matrix C and D, which is a square matrix, non-negative. So ibig sabihin C is greater than or equal to 0, D is greater than or equal to 0. Notations for non-negative definite matrix. Then A result. So if you have one Y, you pre-multiply Y by A. So this is P by N. N by 1 Y. So this is a P by 1 matrix. Man si B is S by N and N by 1. So S by 1 ang BY. So is this conformable? This is P by N and this is N by S. So this is conformable. This is A, B prime is a P by S matrix. So what is this theorem telling us? So kung si AY o si BY daw independent, and this is an if and only if statement, that is when we multiply A and B prime, that is equal to 0. So the advantage of this is that if you have two estimators written as AY, na si Y, and BY, and if you can show that AB prime is 0, then we can say that these two estimators are independent. In your inference, you will see that X bar and S squared are independent. So to show that, we just have to rewrite X bar in terms of Y, in terms of X times some matrix, and S here in terms of X and some matrix B. No? And once you get these two matrices or vectors pre-multiplied to X, and if you can show that A, B prime is 0, then you say that X bar and S squared are independent. So this is the importance of this theorem. So for the proof, so we let a Z, which is your AY, BY vector or matrix. Then you get the expectation of Z, which is just the expectation of Y. So A mu and B mu. And the important thing here is you get the covariance of Z with your generic A, no? Generic A is ito imong Y man i-transform nimo og AY. Imong generic A is AB, no? Para ang covariance of Y is A, covariance of Y, covariance of AY is A covariance of Y, A prime. So this is your A covariance of Y, A prime. So that we see that these two are independent if and only if this is 0, no? Or AB prime is 0. So if that is 0, then we can say that AY and BY are independent. So another extension also, if AC is 0, so kung nakay duha ka estimator na maitsura nimo as AY and the other one is Y prime Y, so this is quadratic in form. If you can show that if AC is 0, so kini na vector din o kini kung imong multiply na 0, then we can say that these two estimators here of this form, so nakakay forma na AY o Y prime CY, these are independent. So in the proof, you will use some properties of a matrix, say C, E prime E, and then do manipulation, no? So you still use theorem 3.13. So, and you use the properties of being invertible of this matrix. So you just go through this proof because this uses some properties in mga properties sa atong matrix being invertible and being positive definite. I will not deal so much on that, and letter C is similar to letter B. And then These theorems only applies if you have idempotent matrices. And then it applies. Theorem 13.B and C also applies for arbitrary symmetric matrices C and D. And the converse of these are also true. So, ibig sabihin, kung naa kay duha ka estimator that are independent, then you can show that it is C times D is 0. So kini siya na mga estimator is in quadratic forms, no? Quadratic forms. Y prime CY, Y prime DY. So kini ang isa linear man quadratic form. And then ang isa is puros linear sila. Okay? So you can show independence of two linear estimators basta mapurma nimo siya inani. Na kay ma-predetermine matrices A and B. Man mapakita nimo na si AB prime is 0, then the two estimators are independent. Also, a linear estimator and a quadratic. Mapakita nimo na siya na independent kung mapakita nimo na kining identified na matrix or vector will be pag multiply nimo it is equal to 0. So this is also true for the other way around. So if and only if statement ni siya. And then the other one is two competing quadratic estimators in terms of y. Man kung ma-multiply nimo si C of D and that is equal to 0, then we say that these two estimators are independent. This is what the theorem is telling us. Okay, so that's it for chapter 3. So if you don't have questions, let me load first chapter 4. Wala na ako na load for a while. So may Shara, you can stop recording for a while because I will be loading. So chapter 4 now we'll talk about the introduction to linear models. So this is actually the regression model, which will be the focus of this course, no? Sa mostly linear models or the basic regression model that you have. So linear models are used for studying the explanation of a given variable y in terms of a linear combination of a given explanatory variable x. So usually when we talk about linear regression model, you have an response variable y or a dependent variable y, and you have an explanatory variable x or independent variable x. So each capital YI will have a realization. Say the particular value will be small yi, I from 1 to n. This will be the realization of each of the random variables of your capital YI, and we call it, as I have said earlier, the response or the dependent variable. And the realization for each of the capital X here will be denoted by small xi, I from 1 to n. And we assume that these x's, this explanatory or independent variable, are non-random or constant or fixed, no? So by assumption, the x's there are fixed and the response will be the random variable. So consider in which we have simultaneous measurement of two variables, x and y. So you have simultaneous observation. So you will have there an ordered pair, no? So for a particular x, you will have a response y1, x1, y1. For a particular explanatory variable x2, we'll have a response y2, and so on and so forth. So often x represents the experimental conditions and y represents the outcome of the experiment. So you have n pairs of observation. So to construct a statistical model for the situation where the relationship between x and y is thought to be linear or approximately so. So if you recall, a linear equation will have say a say times bx, no? So it will have some parameter beta and a here. In other books, you can see this the equal to beta null plus beta 1x, no? But this is just a simple regression. Of course, you can always expand it to multiple regression. So the goal and assumptions are, first, there must be a close distinction between the response and the exploratory variables in regression analysis. And the xi's are fixed in the sense that we consider the conditional distribution of yi given x sub I, or capital X sub I is particularly equal to this realization small x sub I. So what we are doing in linear model is we are actually looking at the conditional distribution of y given the x's. So if you recall in chapter 3, we see there, or we derive there, that if y is normally distributed, y given x is also normally distributed with a tweak in its mean value and its covariance matrix. So usually when we want to see if x and y have a linear relationship, so linear lang gid ang atong ginatanaw din, no? We can always have a non-linear regression, or the general one is the generalized linear models, generalized linear models, which caters non-linear relationship between x and y, but you do some transformation. So that is your generalized linear models. So din here, what we have is general linear model. So it is linear in the sense with respect to the parameters. So kining general linear model, you can see, say y is equal to say beta null plus beta 1x plus beta 2x squared. So kini siya plus some epsilon values or error terms. Kini siya bisan x ang square din but this is a linear model because this is linear with respect to the parameter. You will see later in the report na kini day na model is still linear. So lahi po tong ginaiskot nato na generalized linear models. No, the generalized linear model is the variables x and y there are transformed such that it will have a form that which is linear in the parameter. Although kung tan-aw nimo ang model, dili siya linear gyud na as in giingon nato na ax plus a plus bx, no? Mao man gini siya ang forma na linear. Ang generalized, you can have other form, but you can make a transformation on x and y such that the relationship will be linear. So naana siya sa generalized. Ang appeal ani will be the logistic regression, which is under generalized linear. So if you look at the logistic regression, kung tanaw nimo ang model, S-shape man siya, no? So dili siya linear in nature, but it will be under the generalized linear. Okay. Why it is linear has to do with the link function na you relate x and y. So you will see that later in higher, in other courses that you have. So in here, we consider suitable statistical model, but the relationship between the two is just linear. So in linear models, you will have two versions of it. One is the coordinate-free version, and the other one is the coordinatized version of the linear model. No, coordinate-free version and coordinatized version of the linear model. So let's start with the coordinate-free version. So let V be a given p-dimensional subspace of Rn. Suppose that the random vector yi is normally distributed with mean mu I. Of course, your mean vector mu is composed of mu i's, no? So mao ni ang pasabot kada isa sa imong y, will have its corresponding mu I. Your mean vector is actually in V. So you will see later that this mu, which is in V, is actually the projection of y onto V. This is your mu, no? Na siya sa subspace na V. So, ibig sabihin, kung naa kay vector y, kining vector nimo, gina-project nato into a space V, and we can just look at the mean vector or this projection of y onto V, which is your mu. So this model is called the ordinary linear model. We also call this version of the model as the coordinate-free version of the linear model. So in contrast with the coordinatized version, the coordinatized version is with respect to a basis matrix for V. No? So we let X be a basis matrix for V, then X an n by P matrix of rank P. So ibig sabihin, when we talk about the rank of P, this will be the minimum of the rank of X will be the minimum between N and P. In this case, we choose P to be less than N. So that will be your rank, such that there exists a unique vector beta in RP, so a P by 1 vector, such that you can write a mean mu to be the expected value of yi. So the relationship between mu and beta is given by this one. So mu here, or your projection of y onto V, will be in terms of a basis matrix X beta. Or individually, your mu I will be beta null plus beta I X sub I. So kini imuhang vector dinhi actually is a component beta 1 and beta I, no? So beta 1, beta 2, beta 3, and so on and so forth. So kanay mong beta diha is actually beta null, beta 1 to beta n. So there, your n here is actually p plus 1, no? Number of parameters plus 1 for the beta null. So it is a linear function. Your mu I is a linear function of some parameters here and your explanatory variable x. So that this beta is actually computed in this manner. So x prime x inverse x prime mu. So if you recall, kung generic lang ang imuhang projection, wherein you do not consider an orthonormal basis matrix X, the projection is actually equal to, if you recall, the projection onto Y is actually X prime X inverse X prime Y. No? So if you look at this, if your beta, sumura siya X beta, and then mu is the expectation of Y. So X beta mu. No? That will be in terms of projection. So if we denote this, ano siya, X prime X inverse X prime. No? So this is your beta. So actually, this is just the projection of Y, no, onto the space V of your Y. No? So later you will see that the projection of Y onto V is actually your mu. So this is coordinate free, but in the coordinatized version, you have this. So an equivalent version of the linear model will have a Y normally distributed with mean vector now X beta and covariance matrix sigma squared I. Your beta is P by 1 and your X is N by P. So this should be conformable. This is N by P, this is P by 1. So this is N by 1, wherein your Y is also N by 1. No? So this is called the coordinatized version of the linear model. So ways of defining a subspace. So in succeeding discussion, we use coordinate free version. So sa itong coordinate free, you have a Y normal with mean and sigma squared I, which defines a subspace. So there are two ways of defining subspace. One is you pick a basis matrix, then this is the general linear model of full rank, because when it is a basis, it has a rank. And this is used to define the regression models. Given a basis matrix V and it's spanned by its column because it is a basis matrix. Another way is to define some constraints that the elements of the subspace must satisfy. This type of general linear model, usually when you set some constraints, whenever your matrix X is not of full rank. Usually we see this problem in ANOVA problems and experimental designs model. So the focus of this course is more on the first type of defining your subspaces, wherein you assume that you have a basis matrix. Kini siya another course na po ni siya. Kini when you have a not full rank. So most statistics used in the coordinate free version of the problem can be expressed as projections or lengths of projections. Since the projection does not depend on the basis matrix used or chosen, we can often assume that basis matrix to be orthogonal and orthonormal. So if we assume this, then masimplify to ato ang projection to just because X prime X will just be identity. So ang ato ang projection XX prime, no, will be equal to the projection. Where do you see that? That will be on chapter 2, when your x is already orthonormal basis, that is theorem 2.6. No? So the projection of y and to b will be x prime y. So why is coordinate free more appealing when we study linear models? Because it's not necessary to choose basis matrix X for the coordinate free version of the linear model. Mas sayon siya in terms of notation. And then most estimates used in the coordinate free version of the problem can be expressed as projections or lengths of projections and use of projections, which often simplifies the proof of the theorem. The formula for estimates are much easier to interpret when expressed as projections than when expressed in matrices. And many of the formulas for particular analysis of variance problems are easier to derive using the least squares property of projections rather than equivalent matrix expression. So these are some example of linear models. We have the one sample model, the K-sample model, or also called the one-way analysis of variance, the two-way analysis of variance model with no interaction, and the multiple regression model. So the one sample model is ang katurang model na y is just equal to your mean. Some error term, no? For K sample, then you will have y one-way ANOVA. So equivalently, kini siya mao na equivalent sa test of hypothesis that you are testing that your mu is equal to a specified value. For one-way ANOVA, if you recall, we are testing different mu's there, no? Where there are k of them, no? So this is expressed as y as mean plus some treatment effects or the different mu i's. So these mga treatments ni mo ni mu1, mu2, mu3, no? Plus some epsilon error terms. And the multiple regression, of course, will start with a simple C plus beta 1x, and then if you have many x's, then that will be multiple regression. So the form of the models here will be seen in the reports, which starts with simple regression and then expand it to multiple regression. So our focus here is more on the linear regression models. This one sample is just a subset of the K sample or special case when you have only, you are trying to explain your y as equal to a overall mean. That is one sample model. Okay, so let us see this using some matrix notation here. So kung model ni siya, this is just y equal to theta plus some error term, no? Later you will see some assumptions of the error term. So the one sample model, let y1 to yn be independent, where each of the yi's there are normally distributed, univariate, with mean theta and variance sigma squared. Theta will be from negative infinity to positive infinity. Sigma squared is greater than 0. So this is your vector y and this is your mean vector y. Then in the coordinate free version, you just write y is normally distributed with mean mu, where mean mu is equal to that and variance sigma squared I. Model base, it will be y equal to theta plus some epsilon. This is the model form. So if we define a space for that, so let V1 be the one-dimensional subspace of R to the N consisting of vectors of all whose components are the same. Kaya ang imuhang mean vector is just theta, theta, theta. No? That is this one. For some theta, if and only if your mean mu is in that space, no? The one-dimensional space. Thus, an equivalent version of this model is just equal to this. So, ang mausab lang ani is you have defined where to look at your mean vector, what space, no? So, kini lang, the one-dimensional subspace. So, sa coordinate tree, you just have to identify which space you are going to look for your mean vector. Later in chapter 5, you will see that this mean vector is actually the projection of y onto v. And then if you are familiar with a one-way analysis of variance, so then na may groups of y's. So this is group 1, this is group 2, so on and so forth. This is group K. And then each of the groups will have its corresponding mean, say theta 1 and then theta 2 for this, and then theta K. And here, the sum of the ni's for each of these, this is n1, n2, and then n3, nk. The sum is equal to n. Your y here is normally distributed. So to have the coordinate-free version, so kini siya, ang y explained by some theta i's, no? yi is explained by some theta i's plus some error. But this theta i's here will be a component of the overall theta plus some treatment, no? Kana mga theta diha or ANOVA. Anyway, kini manggod siya is expressed in the coordinatized version, no? Bali ihatagan na nimo og parameters per group here. But here, this is coordinate free. So sa coordinate free, you just define a subspace kung asa siya, no? So here we define V2, a k-dimensional subspace of Rn consisting of vectors whose first n1 components are the same. Then n2 components are the same. So like per group ni siya until the nk. So you have these vectors. So theta 1 lang siya, and then this is supposed to be theta 2 until theta k. If and only if naalagi siya sa imuhang gidefine na subspace. So you still have this assumption on your y, pero ang imuhang mean vector na ana na space V2. So mao tong giingon nila na simple lang ang coordinate free, kay dili ka kinahanglan mag-specify og basis matrix. So if we transform it to coordinatized version, kinahanglan ka maghimo og design matrix, no? Sa imong mga parameters. So what I'm talking about design matrix, let me have some space here. So kung sa design matrix man good, for example, na kay y is equal to a general, sama akong giingon, y1 is equal to theta I plus epsilon I, no? ij na siya actually kay you run from 1 to n. But what you really want is to separate the overall effect plus some treatment effect plus error terms, no? So this one, if we subdivide it into your parameter vector, may mo man na siyang theta plus theta treatment 1, treatment 2, plus so on so forth until treatment K. So para maitsura ni, to make it coordinatized version na kay parameter, no? So na kay matrix A times your parameter, say theta 1, theta ang general. So na kay matrix din man theta, tau 1, tau 2, to tau n. So para ma-describe na siya kini na mga matrix nimo sa kada yij na kay design matrix na himuon ana. So for example sa y1 1. So theta plus tau 1 man na siya plus epsilon 1 1. So pag multiply nimo ana, so unsa may imong design matrix ani para mo gawas na. So dapat 1 1 0, no? 0 na dahil uban para pag multiply nimo bang may mo siyang theta plus tau 1. Man din 0 1 para sa imo ang next na variable 1 2. Pag multiply nimo ang ma-0 ang uban, mabilin din is theta plus tau 2. So theta plus tau 2. So kini na matrix din mo ni tawag ni nato na design matrix X beta na dahil na siya. So if you look, this is your design matrix X, and then this is your beta, which is composed of theta, tau 1, tau 2. So if you look at the coordinatized version ganina, kini, no? This is your coordinatized version. Your mean vector there is X beta. So ang X there, and then beta, say tau 1, tau 2, to tau K. So na kay matrix din na kada model nimo, kada say y11 na kay tau 1 plus epsilon 1 1, no? And then the next 1 2 will be tau plus tau 2 plus something like that. So unsa man ni imo ang X matrix din para mukuha ni na mga models. Mo ni ang coordinatized version. So medyo lisod siya compared atong coordinate free. Kaya ang coordinate free i-identify lang nimo ang subspace kung asa mabilong imuhang parameter. Anyway, we will have more discussion on that. Kanang design matrix usually na siya sa ANOVA. Okay, but for regression dili kayo siya ginagamit. Wala siya gamiton or masayon siya, no? This is two-way with interaction, which I will continue. So one way lang sa ta. This one will be continued next meeting. So two-way analysis of variance with no interaction. So that you will just have an overview of how the data is expressed in terms of models. So kini siya, ang ganina, ang one way, ana lang siya theta plus alpha I or treatment I. Tau akong gigamit ganina. Pero kung two-way analysis na, nanapod kay additional na parameter, kay 2 factors man siya. So beta J. Anyway, so we will continue this next meeting based sa notes. So I will just upload the notes later. Okay.